So the impulse is when we take like a graph like this, and you find that area underneath it.
Right.
So this is the force versus time graph.
Right, so you do force time, force times the time.
Right, if you find like an average force here, you do the average force times the time. So that's impulse equals the average force times the time. And then the impulse is equal to the change in momentum. So change in P equals J equals -12. Then you can relate that to force using time, or using this. Okay. Then the problem is we get the average force and the time. So that might not have been the best way to do it. But if you think about this from like a kinematics perspective, what happens is it enters the target, and this is 40 centimeters. So this is your initial velocity. Okay, 1300. And your final velocity is 800. So if you're looking at your kinematic equation, so like x final equals x initial plus the initial t plus 1/2 at squared, and you've got velocity final equals velocity initial plus at. So given what we know it came in at 1,300 meters per second. We know it traveled 40 centimeters and it left at 800 meters per second. If we can find, what could we find that could help us find the force?
What can we find?
Yeah, from this information.
We can find the area of that. Well, we already know the area of 40.
Yeah, so the distance.
The force.
As far as like kinematics, how are kinematics and forces related? What do we always use for force? Like what was the equation? Yeah, so force equals mass times acceleration. So we know our mass. If we found our acceleration, we could find our force, right?
Alright.
So what's our acceleration going to be here?
Would you do the average? Or would you start with the initial?
Let's see. So we know something about the change in distance, and we know an initial and a final velocity. But what don't we know about this?
The force inside.
Right, and we also don't know time.
Time, yeah.
So we can't use either of these equations. But this one we can. So what's our final velocity?
800.
So you have 800 squared equals the initial
1300.
plus 2. A is what we're looking for. What's the change in x?
It's, oh, 400, no, 500.
Well, that's the change in velocity. But
Oh,
we're talking about just this distance right here,
oh, 40.
right? Do we want to use 40?
Oh,
That's in centimeters.
you want to use kilograms?
Well, yeah, meters.
What meters?
That's 0.40 meters. So whatever this is, you just solve it for A. So acceleration equals something. So 800 squared minus 1300 squared.
Squared minus 13 squared. It's like negative. Like 1,050,000.
Okay, let's see.
And then after that, you divide it by
Oops. Yeah.
0.4.
Yeah, you divide by 0.4 and 2.
That's what I got.
Sweet. Okay. So that's your acceleration. It's negative, right? Oops. There. So that's how much it's slowing down as it goes through this target. It's 1,312,500 meters per second squared.
You know, you times it by mass.
Right. Which is 0.024.
0.024. Negative 31,500.
I mean, newtons. I'm gonna be right.
So that's the speed of the bullet.
That'd be the force that the target exerts on the bullet.
Okay.
Whew. Darn it.
So that's the target on the bullet?
Yeah.
It's not a bullet on the target.
Well, that'd be either one, right? Because if the target exerts it on the bullet and the bullet exerts it back.
Right.
I'm trying to think of this as.
So negative 31,500.
Yeah, well, positive. You'd probably just do the magnitude of it. So then, we found our force. And we have this equation. From before. So how can we use this? This is negative 12 equals force average times time. So how are we going to find time now?
So we can put 31. Negative 31,500.
Yes.
divide that by, well, 12 divided by -31,500.
Yep.
.00038.
So, hardly any time at all. That makes sense, I mean,
So it's going really fast.
what is the target speed just after the bullet emerges? So, you can look at this two ways. Let me, so we found the force, 31,500. Just gonna go like this. So with the bullet, we started, there was a initial, a final momentum, right? And then in the middle, there was this impulse. So what if we thought about the target, and we said it had an initial and a final, and then it had its own little impulse right here in the middle. Does that make sense?
Kind of. Can you say that again? So like would those cancel out, those impulses?
Yeah, they would.
Cancel.
Yeah, if you add them all together, they would. So that's actually the other way to do it. You can look at it as the bullet being an exterior thing that's causing an impulse, or you can just do all of the momentums together.
Oh, okay.
So all the momentums together might be a little easier. So just ignore the impulses. So what's the initial, you said was 31.2 of the bullet?
Yeah.
The P final was 19.2.
Right.
But what? Okay, so you'll have 31.2 as part of your initial. The bullet plus P initial of the target equals P initial, or P final of the bullet plus P final of the target. So what's the initial momentum of the target?
The initial.
Yeah.
Oh, 31.2.
That'd be the initial for the bullet.
Oh, for the target.
Yeah, for just the target. How much momentum does it have?
The 250 kilograms.
Times its velocity, right?
Yeah, and no velocity though.
Well, it's just sitting there.
0.
Yeah.
0.
So this is 0. What's the final momentum of the bullet?
19.2.
And then what would the final velocity of the target, or final momentum of the target be?
We don't know.
Right, but it would be its mass
250 kilograms.
times its velocity. So this is the velocity final of the target. So if we solve for that, then we're good. So you just subtract this over, you get 12 equals 250 velocity final. 12 over 250.
.048.
it's gonna be?
Meters per second.
Yep. Okay. So a bullet comes, hits the target, it's through in less than a hundredth of a second. And then how fast, the target's gonna be moving back just barely, right? But how fast is it moving? Hardly at all.
Yeah, not much.
It'd be like almost 5 centimeters per second. So about move that about that much every second. But it'll slow down immediately, right?